Hello friends, this is Pradeep Kumar. Today we will see the importance of the boundary condition and uh, what we actually apply in the real life problems in any structure. Actually, we are going to model the same thing in the finite element analysis or not. That is the question mark. If we are not going to model the same, so we are going away from the reality. But for a good practice, an FEA engineer must have the closest to the reality. This is the fact. Like a simple problem, very simple problem, you will see, because you know that the construction of any big buildings depends on a addition of one by one bricks. So we cannot deny one bricks, because there is a importance of one bricks. So in the similar way, to do very complex problems, to solve any complex structural problems in our life, on solving that one, we cannot deny the basic concepts, because that is going to be used there in anyhow. That helps in a great way. And after looking this video, I think it's my opinion, you will really appreciate. Yeah, you really appreciate. And I will try to best my to deliver you to enlarge the view of the boundary condition, just and how to model the actual things. Boundary, there are named boundary condition. What is the condition at boundary? That's all. If we have done it, then we are at the closest to the reality. Now let us see the simplest problem in mechanical engineering is the simple tensile specimen. This is a uniaxial tensile testing. This is done in the uniaxial UTM machine, uniaxial tensile machine. This is the simplest experiment in our engineering and simplest case of it, and you know that all these things are derived from here. All the concepts, all the things have been derived from this testing, and big, all these are actually compared with this type of testings, and you know that what is the importance of this. So we are just not diverting other side. We are just keeping the point on the boundary condition and how to just simulate this simple tensile testing experiment in the reality. let us consider a rectangular block or any type of circular block, you can consider it, and we are pulling the machine from both ends of this specimen. Here this one end is here and another one is here. It is pulled by a jaw which is there in the machine, which is going to pull this specimen, and the stresses has been generated in this machine because it deforms, and we get the stresses. There is a internal resistance per unit area, that is P by A, and this is actually linear stress. Okay, after the linear non-linear region there is something different phenomena, but we will not going to discuss here. We are just here we are looking to we are looking we would like to model this specimen. Okay, this specimen, we would like to model this specimen in a simple finite element analysis, and we must get this P by A in finite element analysis, and we know that this is a uniaxial tensile testing, and this is the simple uniaxial stress state condition. So in the whole body there should not be any stress gradients, because stress state is only one, because there is a force P. So only one stress would be present, that is P by A, that is sigma x in the direction of this one. There is none other stresses, means there should not be any gradients. And we will see also, and we are going to model this, we are going to if we are modeling this problem in such a way that we will not have any boundary condition effects in this problem. Like Sand-Vanant principle have said that we are not we will model it very cleverly. We will see it. Let us see. I hope that you would be knowing ANSYS softwares. Here my objective is not to show you the tools and commands of this ANSYS software. You would be knowing these tools and commands, all these things, because it is very common, and but how to utilize this and tools and commands, and how to do this tools and commands to simulate the reality, that is my task. Because if you are doing only understanding the tools and commands of modeling and FES software, then there would be no difference between you and an operator, computer operator. Simple model, we have just a rectangular, we are making this a rectangular specimen. Okay, so actually this is our we have to remove this one, by mistake it has been drawn, and this length actually 3000 mm. We are taking this mm as we take this mm as 3000. Which one? this this length has this 3000 means 3 meter. Okay, this length is we are taking 1000, but it is very long specimen, so we are going to reduce this one, not 3 meter, it's very long. So we are taking 500 is this and 200 is this. Okay, or 250 you can do that one, half of, yeah. Yeah, because it is looking very small. So what we are going to do, we are just removing this dimensioning patterns, and we can see that this will fit in the whole screen. Create sketches, create surfaces from sketch, and then generate. We have generated a surface. Now next, go to the modeling. There we will apply materials, boundary condition, meshing, all these things we will do. So we are going to apply a boundary condition here. So let us look at this boundary condition. Okay, so it is just coming, yeah. Just give it, because you know that no other body is having the 0 thickness, just have 1 thickness. Okay, and just simply mesh it, because it is very simple body, so meshing will be done very easier way, because today's lecture is not about the meshing, it is about the boundary condition. So some refinement you can also be there and do that, some refinement, but need not necessary, we will see later. Now next, the most important thing is the boundary condition. What do you think? How should we apply boundary condition here? We know that at this end there is a grip. Okay, there is a grip, which is grip or clamp, which is clamped here. Something you can do that of some regions of this has been clamped. So one assumption we can do that from here to here it is clamped. Okay, so what should I do? Should I fix this line in all the degree of freedom, like fixed support? Should I fix this line in all the degree of freedom? Let us do that. I think you would be having in the mind, yeah, you should fix, because this part is actually gripped by a gripper. So this is just fixed, you would be having in the mind, and every one person would be having. So I am doing the same way. Then look at the things, and at this end we are applying a force which is having a magnitude of anything you can do that. Let we are having the magnitude of 50 kilonewton. Okay, 50 kilonewton, 1 2 3. Okay, 50 kilonewton. Using this 50 kilonewton, see, the stress should be in the body 50 1 2 3 by area of cross section. We have taken the thickness 1 mm and its width was 250, so stress should come 200. Okay, so stress should come this value. Now let us see. We have applied this amount of force, and we are looking not direction, you want to see also the direction. We are looking the equivalent von Mises stress. We know, you would be knowing what is equivalent von Mises stress. So actually you know that equivalent von Mises is actually the square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, and it's all multiplied by 1 by root 2. In this case, this is the uniaxial loading conditions. In the because this is uniaxial loading condition, so and sigma 1 in the von Mises stress, sigma 1, sigma 2, sigma 3 is the principal stresses, and you know that what is the principal stress is the stress this principal stress are actually developed in the principal plane, and principal plane is the principal stress. Actually it is the normal stress, which normal means the normal of that plane in which the shear stress is 0. So in this case force is applied here in this direction, and the stress, shear stress in this plane is actually this plane perpendicular to this force 0. So this plane would be the principal plane, and this stress along this x-axis would be the principal axis. It means this axial stress, which is P by A, is actually the principal stress. Unfortunately, means it is there, but in case of triaxial stress rate it will be different. You know that from motorcycle you can do that, but here this plane is actually principal plane, and this stress is the principal stress. From that, if you calculate the von Mises is going to be equal to be the sigma x, and we have derived that, we have calculated from calculator the sigma von Mises or sigma x should be 200, but it should be 200, and this 200 is actually should be throughout this body, no color pattern. There should be no color pattern. Okay, like this here there are, you can see the multiple color patterns have been arrived here. Red is saying 214, and at this region definitely away from this boundary condition you will get approximately value 200. Yeah, you are getting 200, so you will say yeah it's okay, 200 we are getting, but in this analysis the effect of boundary condition has been included in this model. Okay, let us, you want to be get a converged value. Let us do for convergence of this stress. %1 difference, and maximum confinement loop is 5. Solve it. Okay, after next refinement level, when element was total element in the body was 66, then we are getting stress 214. When total number of elements in the body is 264, then we are getting 246 stress. Again the stress has been increased to 289, and the element, this 289 is corresponding to the element, total number of element is 1051. Okay, again the stress we have increased 341. And you remember that we are not increasing any load, we are just refining this element. It's just refining. When you are looking at the number of elements, as the number of element is increasing, we are getting the equivalent stress has been increased. So in this way we have seen that after 5-6 refinement, we are not able to get the converged stress value. We are not able to get the converged stress value. And where is the problem? Here is the problem, at this point. Yes, there is the problem. These are the 2 points, and I am telling you, keep it the infinite numbers, infinite number of elements, you will not get the convergence. Because what is the reason? Because at these 2 points singularity has been created. What is the singularity? Mathematically, singular point or singular region in any body is the point or is the location where the stress is infinite mathematically. So why it is increasing? I am just telling you why it is increasing. It is increasing because mathematics says, finite element mechanics says, when singularity exists in the body, stress at that location would be infinite. So same thing is done by this FEA. It is achieving this infinite value. It is achieving, means it is moving towards this infinite. But now come to the reality. In reality, can be happen infinite stress in any material for this given loading? No, not at all. So what is this? So this is called garbage output. This is nothing but a garbage output. 477,400. It is not a real value at all. This doesn't exist in the reality, and which doesn't exist in the reality, which is the garbage output. So this comes because of the garbage input. Garbage input can be in any types, either you have putting the wrong boundary condition, you have putting the wrong forces or materials context. There are so many things. You think on you think on that this is clamped by 2 ends. So clamping means fix. We have applied the fix. We are pulling one side, because you know that we cannot pull by both the ends. We cannot do the force. We cannot do that we would apply force on at both the ends, and then because you know that the stiffness matrix would become singular. So singular matrix inverse is not possible for singular matrix. That's why you have to apply a boundary conditions at boundary. You do that. You have to do that. But you know that you know the physics of the problem. You know that stress if it is pulled by, if it is pulled uh, by at the two ends, the stress must be this 200 value, but it is not coming. And in addition to that, um, there we are, if we are refining it, and we are getting this higher and higher, and then how we decide what is this actual stress in the body, and how do you get that one value? So we have to apply the correct boundary condition. How do we do that? First, don't apply this fixed support. Don't apply this fixed support. You apply a displacement boundary condition, pick this as, and here you just keep the x displacement in x direction is equals to 0. If you solve it, then it will not going to solve, because matrix again would become singular. So to actually, why I have done it? First question, why I have removed this fixed and I have done this just only apply the displacement boundary conditions in x direction? Because just think on the free body diagram of the uniaxial tensile test. Free body diagram says, if you apply force here in this direction, at this end there would be a reaction force. This reaction force is generated because of this, at this boundary, because of why? Because we have stopped this boundary condition, means there is some supports here, and the direction of the force in this direction, because of Newton's third law, equal and opposite direction. The force is not coming in this direction. Force is means reaction. Force is not coming in the direction. Reaction force is coming in this direction. Okay. So in the opposite you can think, when the reaction force is coming in the direction, so we must apply the displacement boundary condition in this direction. When the force is still not coming in this direction, then why we are going to apply this boundary condition in this direction, in y direction? As per the mechanics, we know that if any body is pulled in uniaxial direction, the reaction force would be in the same axis. The reaction force could not be come in the perpendicular to that, because the force is applied in simply the reaction would be in this direction. Reaction is coming in this direction. It means reaction. It means why the reaction has come here, because of we are stopping it here. We are stopping it here. We are cutting a section, and we are thinking that this half of the body is under equilibrium. This body is under equilibrium because a opposite forces has been applied in this at this face, and the direction of this force would be this opposite to this, the direction of this force. So because of the limitation of the finite element, because of the singularity matrix has been created, so we cannot apply the force in this direction. We have to apply boundary condition. The boundary condition, the direction of the boundary condition, because it is also a vector quantity, so it must be the same direction as per this force, and if there is no force has been generated perpendicular to this direction, so why we are going to apply force in this direction? Simply, so I think you have understand that we have made a mistake. We should not apply the boundary condition in this direction. If you solve it this problem, the FEA will not solve because of the because still this matrix would be singular. So to just avoid the singularity, just take it one point and give it to the fix in the y direction. Okay, and solve it. Okay, so this is the equivalent stress. You can see here 200, 200, 200, 200, 200, 200. Okay, so this is the boundary condition which is applied. This is the stress which has been induced in this body, and as per our calculation, the induced stress in the body should be 200, and if we apply a force which is having value P and the stress is P by A, and if it is uniaxial stress state condition, so the stress at each point in the body should be P by A, because I am telling you the normal stress or von Mises, I am telling you, not the stress in other planes or other coordinate axes. So because the force at each point in the x direction is P. Okay, so stress at each point in this body will be P by A. So this would be same throughout the body, and if we have a capability to avoid this effect of boundary conditions, so it is very good that we have done it here. We have modeled in such a way that we have avoid the effects of boundary condition, and we get it the 200 value throughout this body. So this is really nice. This is really nice, and you can also study the convergence of this stress value. I am changing with 1%. Allowable change is the 1% from previous, and I am just 5 number of refinement loops. Refinement depth I am taking 2. You can take the same and just solve it. See what is going to be happen in the next refinement level. In first refinement there is a 66 elements. In the second refinement is 264. 264 elements, and the change in previous is nothing. It's 200, 200. You can see it's 200, 200. Nothing change in all the body. It means this value is a converged stress value. So first thing, we have modeled it correctly. Second thing, we have avoided the effects of boundary. We have avoided the effects of boundary condition, which is told by the Sand-Venant. Sand-Venant said, if you grip it to anybody and apply the force at the boundary, there would be the boundary effects, like that he said. And so in the simulation we have modeled in a very very cleverly way that the boundary condition if we avoided and we get this stress Vy in all the body, and that should be actually. Thank you very much for watching this video, and in this same video we are going to continue a thermal stress analysis. Very interesting, very interesting. I will take a very few minutes for you to perform such analysis, apply a thermal condition in this body and give it to 200 value. Okay, or I am thinking okay, apply the 200 stress in this body. So let us apply this displacement to 0. What I am going to study here, just delete this source here, delete this source here. We are going to see the two things. First, the same. Let any body has been fixed at it means we are gripping at one end, and we are applying uniform temperature T in this body. So what is going to be happen? And you know that and we are only just gripping at one end, and you can see what this stress is actually coming, and here we are applying all 0 because we are gripping at one end. It means so it is not solved. Okay, do one thing, just fix it here, not solve it. Now equivalent stress is coming actually 524. What is that value? You know that this would be the thermal stress, and thermal stress is actually epsilon alpha delta T into E, and the alpha for this material is steel. It is 1.2 into 10 to the power minus 5 degrees Celsius, and T we have given, that is 200. Okay, and environment temperature is 22. Okay, and E value is 2 into 10 to the power 5. So what would be the thermal stress in this? What should be the thermal stress? So its Young's modulus of elasticity is 2 into 10 to the power 5 multiplied with, and we know that 1.2 into 10 to the power minus 5 and plus 5 will cancel out, and 2 into 1.2 into 200 minus 22. Okay, it's 178, I think you can do that one. You can do that one. 200 minus 22. Okay. So if you will multiply all these things, you will get 427.2. This is the thermal stress. But thermal stress should present only in those cases when it is restaurant, and it is coming 524. So we have fixed that one, and it is deforming in this direction like this, and this value is coming something different, 524 like that. What is this? So again it is a garbage output. We have to understand the phenomena of the thermal stress analysis. If you want to actually picking at one end, and still will not, if you are not stopping the strain in any one direction, then we will not getting to stress. But here we have fixed and we are allowed to move, but still we are getting the stress. That's because of the incorrect boundary conditions. So what we are going to do, just remove. Actually this case should be the free expansion case, but we are not able to simulate this free expansion. So free expansion case is that is the displacement boundary condition, and here apply this x force in x direction. It should be 0, and displacement at this point is in y direction. You keep it 0, okay, because it is a cell element, so you can have the fixed rotation of this body, okay. So you just pick it fixed rotation and just solve it. Okay, so if you see, if we will see, if you see the stress value in this system, so we have applied this 200 degree centigrade, we have applied a displacement boundary conditions in x direction, and y z is free, z is remaining, and here for solution purpose we have applied the boundary condition in y, and if you are looking equivalent stress, and it is coming near about 0. This is called a, you can see, this is called a free expansion case. This is all on 0. So that's I am telling you, this is the effect of boundary condition, because this thermal, in case of thermal stress analysis, the stresses will only be induced when it is restricted. Okay, so we understand that yeah, it is not restricted, it is just it is the free expansion case is and if you do the free expansion case by doing previous manner, then we cannot do that one, we will get some garbage value. Now next, how do we get this stress, and how do we get this stress value 427.2? We can get this stress value if we'll, and this should also be same in whole body, apply a boundary condition in such way that if you apply fix here, again you are making the wrong thing, so I am not going to repeat that one, I am just applying the correct boundary condition, and in this y direction, sorry, in x direction, is equals to 0. Okay, so and then solve it. Okay, so we are getting, you can see here exactly we are getting 427.2, which is we have calculated from E epsilon alpha delta t. Okay, exactly we are getting, and the deformation you can see that this is, we have restraint in this direction, and because of thermal growth it is moving in this direction. Okay, the stress is coming because of these two supports. Let's do, if we'll fix in this direction, fix it means let we are stopping the displacement of this direction, what amount of the stress should come? According to the thermal stress, you can think on that. It should be epsilon alpha delta t, because if you are not changing the temperature, if you are not changing the alpha, if you are not changing E, then it should be E epsilon alpha delta t. But the scene would be something different. What the scene is going to be happen? It is displacement. Okay, and pick this boundary and y keep it 0. Okay, and I think we should take this edge also as y is equals to 0. Okay, and this is x is equals to 0. This is again x is equals to 0, and this is not needed because we have also done in x. This is also in y direction, this is in x direction, this is also at this. Now solve it. Okay, so actually what we are doing, we are stopping actually the deformation of this thermal of this body due to thermal expansion here, and also in horizontal as well in vertical direction. You can say that this body is not going to be deformed here in the neither in horizontal nor in vertical direction. It is just deforming like this. So in this case the stress is coming 610.29, but according to, if you see, as for the things, according to thermal stress theory, it should be 427. What is this? So I am telling you that if you will get the reactions at these two boundaries, first is the displacement 2, this boundary. Okay, and again get the reaction at another boundary at, here displacement number you can tell 5. Okay, so solve it. Actually should be the resultant, it is giving the resultant, so we have to do something. Here you can see the resultant force at this boundary is coming 1.5 to 57 into 10 to 5 Newton, but here because at this both are we have modeled with the same, that's why the resultant is coming is 0. So we have to do one thing, model only one edge. Okay, one edge, and just unsuppress this one, unsuppress and model it with this one to get the boundary reactions in y0 and other must be free. Okay, there must be free. These are the just correct boundary conditions, and now solve it. So we will get the reactions force at here and at this vertical edge and horizontal edge. So this is the reaction force at horizontal edge, and this is the reaction force. It is the vertical edge and this is the horizontal, and you can say the directions also. And this is the value which is coming, this total value. Okay, you can see here this is 3.05 into 10 to the power 5, and this is 1.5.25 into 10 to the power 5. You feel, and you can say that you can see here this stress in this force in this direction. So you can get the stress in this direction, and also so this is and also you can get this stress. So this becomes the biaxial stress state condition. Okay, the previous case we had fixed here and here, it was the uniaxial stress state, but here we have fixed in all the four edges, so it becomes the biaxial stress state condition. So here sigma x, sigma I, sigma x, and this is my y and sigma y. So if we calculate sigma x and sigma x at this due to this force, sigma x and sigma y due to this fx and fy, and these are the biaxial stress state. So the sigma x and sigma will become sigma 1 and sigma 2 principal stresses, and because this is 1 minus stress, so it is actually equivalent stress, means 2 under root sigma 1 minus sigma 2 का whole square plus sigma 2 minus sigma 3 का whole square plus sigma 3 minus sigma 1 का whole square. It is actually this value. So if we will calculate the stress sigma x due to this fx, sigma y due to fy, and then this sigma x and sigma y will become sigma 1 and sigma 2, because in this plane there is no shear stress, and also again in this plane there is no shear force, shear stress, only one force is there, normal force, because of this expansion. So we will get this equivalent stress value 610. So I hope you have understand that how the things has been changed. Actually there is no ANSYS thermal thing stress in the calculation. It is simply if we had applied only the vertical supports here, so we are getting something stress 427. So that stress, if you see, if you will get this reaction force and divide the area, then you will get again this value stress 427. So in the finite elemental calculation, it is based on reaction force only. So it was uniaxial stress state, that's why 427, and it is a biaxial stress state, that's why it is coming 610 value. So these are the values which are getting. This is actually the closest to the real, not close. This is the actual value which is coming in the body. So that's why we have, therefore we have modeled the FEA model as the real body, and real deformation phenomena, and really how the body is going to be behave and all these things. If and these are all the converse value. If we will apply the incorrect boundary condition and all these things, so you will be in trouble, and then you will think, what is this? Yeah, this high stress 1000, 2000, what is that? And you will be get confused. So be aware with applying boundary condition. I have shown you the importance of the boundary condition in very simple case, and now you can use your brain to apply this concept, this understanding for your any type of complex problems. Piping case, it is gas is flowing in the pipe channels, anything, anywhere you can apply this thermal stress analysis concept or static structure analysis, anywhere. I hope you have enjoyed this video, and I have uploaded this video because I felt that this is very small thing, but it has a very depth penetration. So I think it's very fantastic. Thank you very much for having looked up with me, and giving this time for me. Thank you very much.